Hi, my name is Jasper Bongertz. I'm doing network analysis when I can. Very often I'm not doing network analysis because I'm doing other stuff. I have a slide about me, and let's see if that's working. So, in my normal life, I work for Airbus, the guys with the airplanes and other stuff. I do a few things in the Wireshark community, including writing a blog. I have a Twitter handle, and I'm quite active on the ask.wireshark.org Q&A page, which I highly recommend if you have questions about how Wireshark works, why something doesn't work, if you have an analysis problem where you need some help, that is the page to go. And of course SharkFest, but since you're here, you already know that. And then there's a small tool I wrote called TraceRangler, which I'm going to be talking about this afternoon, mostly used by other instructors to sanitize their trace files and remove sensitive information, but that's something for another topic. So, my rules of engagement for this talk. This session is no slides. Well, you're seeing some slides right now, so there are slides, of course, but there will be no real content slides. It will be interactive. So basically, I'm going to run Wireshark live, and we're working with it, and see how far we get. This is beginner level, so if you're advanced like Vladimir here, you can be sitting here, but if you're giving me all the right answers on the first try, I will stop listening to you, because I want everybody to check out the problems, and you don't need to have the right answers. Please, if you think you have an idea about what the problem may be, just let me know, even if it's probably wrong, it doesn't matter. I want you to basically learn from going back and forth about various ideas and sharing and finding out what it really is. And if nobody's saying anything, or if Vladimir is always giving you the right answers, this is not going to be fun. So Betty is probably not going to be listened to as much as well. We're going to work through the traces. You can give false answers if you know that they're false, if you want to. Oh yeah, great. But what I want you to do is basically work with me, see if you can find something, give me ideas, and I will help you. If it's not the correct idea or not the 100% correct idea, we will refine it until we get an idea what's happening. And I have to tell you this as well. Not all the traces I have with me, I know 100% what's happening in there, because if you're doing network analysis, there's only so much that you can find. Usually we stop at the point where we think we have the main problem identified, but there may be so much more. And I was giving Wireshark trainings for a couple of years, and usually it happened to me even after doing the same exercise a couple of years, somebody would find something new. That is quite normal. I think that happens to Betty as well. Somebody comes up and, hey, have you seen this crazy thing? And you're like, what? Why? No. So that is quite normal. So even the ones of us who have done a lot of trace file work, we don't know everything. Sometimes we're wrong, and don't let that stop you if you think you're not the perfect analyst, because that's what the session is for. I try to get experience into your head, because you can only get experience by making mistakes and finding things out after they were used or needed. So that's what we're going to do. Also, I have to say, I wanted to have this time slot because that's usually Hansang's slot. But he can't be here because of other reasons, and this is why I'm taking over and trying to be a good replacement for him. Alright, so let's check out some PCAPs. I don't know if any of you downloaded the PCAPs before this. Who has downloaded them? 1, 2, 3, 4, 5. This is 6. Wow, 4 people more than in the US. When I was in the US, I was acting like, who downloaded the trace files before? And there were 2 people like, a room full of people, and 2 people like, okay, why am I putting them up there? I don't know. But you can get them if you want to. maybe I should post the link again. So if you want to, you can run Wireshark on your laptops right now and work through them with me. But you can also watch them on my screen and go through them with me, however you like it. I think I put them somewhere on my blog post. There it is. So it's blog.package-foo.com/sharkfest-2017-hands-on-files. Should make that more complex, so it's even more difficult to write. So if you want to grab the trace files there, you can also watch the session just now and get them later, however you want it. I think I should copy the URL and put it in a notepad somewhere. So, I'll give you a minute if you want to download them, and then we'll start. You can also take a photograph of this URL, but that won't download the file, obviously. Okay, so while we wait for people to type in the damn long URL, who thinks he's a beginner? Okay, the rest is experts, right? Because if you don't raise your hand, I'm like, okay, then you're the other thing. Okay, so don't be afraid to raise your hand because we are all learning every day. So once again, who's a beginner? That's better. All right. So me too, sometimes, depending on the protocol that I'm looking at. All right, so who's still fighting with the download? Who needs more time? No hands? Okay, then we can start. All right, so I have a couple of trace files that we can go through. And I named them sample 01, 02, 03. Of course, they weren't called that when they were captured. The names were much more precise, telling me what is in there. But if I would have the names of the PCAPs with what's in there, everybody would know, oh, this is this problem. So I renamed them to sample 01, 02, 03. And well, this is how Wireshark looks like when I open it. Who has the same picture in front of him right now? Same colors, same setup, same everything. Okay, who has a different one? Okay, good. This is basically the initial Wireshark setup that you get if you install it and run it. Who has been to Laura's class? A few, okay. So she probably told you to change a couple of things. I'm telling you the same thing. The standard Wireshark setup is okay-ish, but nobody that I know that does network analysis really uses it in that way. Everybody changes it at some point. So I have my own setup that is quite different from this one. I can show you this, and I will be going back to the standard one after that. This is how mine looks like. What I do is I want to have a full height packet list. This only works on an HD screen or more. And I have my decode on the upper right and the packet bytes on the lower right. You can even remove the packet bytes if you want to. I sometimes need them, so I keep them in there. And my coloring rules are completely different from the standard ones. If you want to, you can get my color rules also from my blog. They're also there somewhere. And they look a bit like this. So over the years, all the stuff I found, and it's really small, I know, you don't need to read it right now, you just need to see that there are a few of them. Over the years, I collected stuff that is interesting and made a color rule of it. So the idea is to have stuff that is a little bad yellow, more bad orange, really bad red, and stuff that is nice and cool, like green, blue, whatever. Yeah, so the redder it gets, the worse it is. But not always, because packets do lie sometimes. I think everybody heard packets never lie. you can remove the never from that, because sometimes they do lie. So you have to check it in most cases anyway. But it gives me an idea of looking at the trace without the crazy colors, which are the default, so that I can see, well, there's something in the beginning that seems to be not so cool, but in the end looks better. So I get a quick idea where to look. Okay, so before we go into this one, I want to open a different one that is not in the download, but it's just there, or I'm just using it to go through a few things, because I think we should look at things working fine before looking at things not working fine. All right, so let me arrange some of the columns. Length is okay. All right, so this is a very simple trace, for me at least. What you can see is you have a three-way handshake at the beginning. Who doesn't know what the three-way handshake is? Does everybody know? So everybody knows SYN, SYNAC, ACK, three-way handshake, right? Okay, how many things can go wrong in a handshake? A million is maybe a bit much, but you're trying to be on the error side, of course. A couple of things, all right? So the things that can go wrong is the SYN isn't received, or the SYNAC is not coming back, or the sequence numbers don't really match, or there's a CSC error in there, or whatnot. So there's a couple of things that can go wrong. This is how it looks like when it works. So we only have one green packet on the top, which is the SYN packet. I color them green because a new session starts, a new live is beginning, so that is green. So, nice one. And the fin is like a nice way of saying goodbye, so it's turquoise, some sort of, so basically saying goodbye in a nice handshake kind of manner. If there would be a reset, which is quite a common way to tear down a connection, it would be yellow, because a reset can also be a sign of trouble. So it's more in the yellow. So basically what happens here is that I'm going to have relative sequence numbers, which makes it easier. Relative sequence numbers, everybody knows what they are? Who doesn't know what relative sequence numbers are? Everybody knows? Okay. So as you can see, I have a SYN up there with a sequence number of 0, and one trick that I often do when I want to focus just on a few things is filter out all the rest. Okay, so right now I want to go quickly over the three-way handshake, so I don't need the rest of the packets. So what I do is I put in here a filter saying frame.number less than 4. It looks like this, frame.number less than 4. And now I only have the three-way handshake visible, so the rest is just not shown and can confuse me. I use that sometimes to remove stuff that I don't want to look at right now, because often you look at the wrong packet and then get confused. So if I just want to see how's the handshake doing, frame.number less than 4, meaning show me the first 3 packets, and then I have it. Of course, that only works because the handshake is the first thing happening in the trace file. If there would be frames before that, I would have to include an additional statement saying it needs to be greater than this and less than that. So like a range kind of filter. Okay, so what's happening here is the client with the 124.100 sends a SYN and says, hey, I want to talk to you. It has a sequence number of, in this case, 0, which is not true. It's much more complex than that, but we're using relative sequence numbers, which reduces it to a 0. So what Wireshark does basically is look at the SYN packet, takes the big number that's in there, and subtract that from every number it finds for that client, so that we have a relative number of growing sequences. It's much easier to track it that way. The only danger that happens here is that in the SYN ACK, here you can also see there's a sequence of 0. Yeah? But it's not the same 0 as the SYN packet, because every side has its own sequence number. So relative sequence number have the one danger of confusing you with two sides being very close to each other. If you're looking at the absolute sequence number, that usually can't happen because they're miles away from each other. Now we can check that real quick. I'll go over to the protocol preferences and say, instead of relative sequence numbers, I'm going to say, here's the absolute ones. And here you can see it's sequence 41 something, and the other one has 97 something. So they're very different. But for relative sequence numbers, they get very identical. So if you're using relative sequence numbers, be careful that you don't confuse them. Okay, let's do it again. So what happens here is the first guy says, SYN, hello, I want to talk to you. I have a sequence number 0. The SYN flag counts as 1 byte, so we need to increase the sequence number by 1. It's like a so-called phantom byte, or whatever you want to call it. So the next guy answering needs to acknowledge that number, right? So I'm sending SYN 0, there's a +1, so acknowledging that packet means somebody needs to send me back an acknowledge of 1. If that's the case, everything is fine, handshake looks good. I send back the final ACK. Now I have a sequence of 1, which you can see in the last packet, and an ACK of 1. Why is the ACK also 1? Any idea? The other one sent back a 0, and? Yeah, but why is it a 1 and not a 0? Yeah, louder? Yeah, because there's a SYN flag in the SYN ACK as well. So that means increase it by 1 as well. So whenever you see a SYN flag, 1 byte needs to be added to the sequence number. Or not 1 byte, but a 1 needs to be added to the sequence number. It doesn't matter if it's a SYN or a SYN ACK. If the SYN flag is present, increase the sequence number by 1. Is there any other flag for which that happens? Does anybody know? Or are all the other flags like don't matter? Does it happen for an X flag? Any idea? No? Okay. No, you don't. Yeah, for an X flag, you don't increase the sequence number. You can easily tell by the last packet that we see, it has sequence 1, ACK 1, and the packet before that had SYN and ACK set, but we only increased the sequence or the ACK number by 1, so the ACK obviously doesn't matter. We know that the SYN matters, but the ACK doesn't. Okay, so is there any other flag that also matters in a way like the SYN flag does, or are all of them irrelevant? Any idea? Okay, yes, there's one, and it's called the fin flag. Yeah, for SYN and fin, you need to increase by 1. Everything else, we don't care. Okay? It's not really that important, but you kind of should know. Good. So, I just wanted to get that out of the way because we are going to look at some of the problem trace files now, and the handshake sometimes is a little strange. So I wanted you to see one that's working perfectly, because the next one isn't. Okay, I'm going to remove my packet bytes thing here and increase that a little more. So this looks a little overwhelming, but it's not that many packets. I'll give you some time to look at it, and maybe somebody can tell me strange things. I don't want to have the right answer why everything is broken here or why something would be broken, but just let me know if you can see anything that is weird or seems to be wrong. If anyone has anything, just let me know. Yeah. The SYN ACK doesn't come? the SYN ACK doesn't come back in time, or for whatever reason it doesn't show up where it should be. It should be the second packet, right? It doesn't, so apparently we have another SYN because nothing happened. And why do you think the SYN ACK didn't appear? Or why was the SYN sent again? Something is missing, yeah, but we can tell by the delta time column how long did it take for the SYN ACK or the SYN to be sent again. 3 seconds. This is something where every network analyst is like, this is not good. Because 3 seconds basically is a very long time. It's an eternity in network timings, so to speak. And also, if you see something like a 3-second delay for a SYN, you know that that is a retransmission triggered by some kind of timeout, where the sender of the SYN was annoyed that the SYN ACK didn't come back and said, well, if you're not talking to me, let's try this again. Okay, so this is a retransmission of a SYN because no SYN ACK was received. Not in time. Okay? All right, so something else? Anything? Does the SYN ACK come back at some point in time? Which packet? Number 3. Okay? It's red. Why is it red? Well, it's a little hard to see probably because I increased the font size so much. Can you see anything in the info column that is odd? Window size, what is that? 0, which means? Okay, you have no receive window, and that basically means don't send me anything. All right? So it's like, hey, I want to talk to you. Hey, I want to talk to you too, but don't send me anything. That is what 0 window means, right? Yeah. So everybody knows what the TCP window is. Telling the other guy how many bytes you can receive in one go before having acknowledgements coming back and forth. It means that if we are talking to each other and you're like, hi Jasper, I want to talk to you, and I'm like, hi, don't talk to me. It's kind of not really helpful. It means that this connection is established, sort of, but one has a gag in his mouth, like, you can talk to me. We're talking with each other, but don't send me anything. That doesn't make much sense. So that is the reason why this line is red. By the way, if you ever want to find out why a line is colored in a certain way, do you know how to do that? How to find out what coloring rule is the reason? Because there's a lot of red stuff in there, and red is applied to a lot of rules. So what you can do to find out which rule applied to the SYN ACK here, you can go into the frame decode, and down here it will tell you that this is a invalid TCP packets color rule, and the rule here is the TCP flags.syn is 1, so the SYN flag is set, but the TCP window size is 0. I have a color rule that tells me, hey, here's a SYN flag, but by the way, the window is 0. That is something that shouldn't happen, so red color. Now, if you ever wonder why something is colored, go into the decode, look at the frame header, and you'll see the rule that is applied. And if you think it's an error, you can change your coloring rule. Okay? So, what is going on next? We see a SYN, a retransmitted SYN, which means the SYN ACK is coming back later than it should be. Why is that? Whose fault is that? Is it the fault of the SYN guy or the other guy? Well, who didn't send what he should have sent? Or the other guy, right? So I'm sending something, let's say, to a server, and the server doesn't answer. Well, it's not my fault that the server doesn't answer, so it's the server's fault. So I send my SYN again, and then the SYN ACK comes back with a window size of 0. Whose fault is that? Mine or the server? Server again, right? because the server is basically telling me like, don't talk to me, we're going to have a session, but don't speak. Okay, so the server seems to be the bad guy here. And it is, I can tell you. So the next one is number 4, it's just an ACK. Is there something strange going on in that ACK? Checksum incorrect? Yeah, the checksum is incorrect. Is that a bad thing? Do you think checksums should be correct? Who thinks checksums need to be correct all the time, otherwise we have a problem? Oh, like, okay. You need more coffee? Okay, so what are checksums good for? To prove that something is not broken, right? So do you want to have broken stuff? I don't want to have broken stuff. So yes, checksums need to be correct. It's not correct here, but this is not because the packet itself had a broken checksum, it's because the capture was capturing the incorrect checksum. Now that is something that happens a lot if you capture on the machine that is in the communication. So if my laptop is talking to someone with a TCP connection, and I'm capturing that on the laptop while it's doing that, the checksum will almost always be incorrect because they're not computed at the time that Wireshark picks up the packet. Which is why, when I get a trace file where one side is having all the incorrect checksums for every packet, I know that somebody captured it on the device that did the communication. So a broken checksum is only a problem if you can't explain it. And in this case, we can try to check who has a broken checksum. So there's another trick here that we can use in the future. You can see here the red line checksum is incorrect. Yeah, and it says bad checksum. And we can try to filter on that and say apply as filter, select it. So in this case, all the checksums except for one that are broken are coming from the 192.168.0.1. That's interesting. The screen is so small I can see it. So it was that. So usually you can basically click on a field and say, I want all of the packets that have the same thing. This like this. Just select any line in the decode, right-click, select as filter, and then it will be applied. So we have a couple of checksum errors here. In this case, most of them are on the 192.168.0.1. So yeah, there are some problems with checksums, but if they would be really bad, everything would be not working, because if the TCP checksum is wrong, basically the receiver needs to drop the packet, and that doesn't happen because we see that the communication at some point is starting. Luca? Yeah. That is a good question. Very often, if the checksum hasn't been computed yet, like I told you before, if you capture something on the laptop that is sending the data and the checksum hasn't been computed yet, it's 0. Very often. Sometimes it's not even 0, it depends on the system that you're capturing on. I have no idea where this one was captured because I took it from the askwireshark.org page. So I don't know why it's not 0. Here's an interesting thing that you can see at the checksum. It says the checksum of 536F is incorrect, it should be 536E. It's off by 1. The reason for that is that I sanitized this trace file, I use traceringer to remove sensitive information. And there's a problem when sanitizing trace files, because if the checksum is bad and you want to keep it bad in the sanitized trace file, you cannot just randomize it, because by mistake you may be writing the correct checksum. So what I did is I calculate the correct checksum for the sanitized frame and increase it by 1, so it's bad in every case. So if you see a checksum that is just 1 wrong, or just wrong by 1 byte, it's because the trace was sanitized. Almost always the case. Yes? Yeah, you have checksum unverified because so many people are capturing with Wireshark on their own laptops. That is basically like 95% of the time people are doing that. They're capturing on their own systems, which always generate broken checksums. And guess what? These people will ask the developers, other network analysts, why are my checksums broken? And the developers got so annoyed by it, I think, that they turned off the checksum checking so that they don't get the question anymore. Okay? So what I did here is you go into the protocol preferences, and you will see that probably validate the TCP checksum, if possible, is not checked. If you check it, congratulations, you will have bad checksums. Okay? Good. We learned something. Yeah.
It's also caused by an issue that started back about 2005 with an option in cards called checksum offload.
That is exactly why it's happening.
Enabled by default, you can go into your new card settings and turn it off.
Yeah, you could do that, but that doesn't make that much sense. I mean, yes, you can do it. Basically, the reason why the checksum is wrong. Back in the day, the CPU did everything. So the network packet being prepared was computed by the CPU completely, including the correct checksum and everything, and then sent to the network card and sent out. Since our networks got faster, the network card is doing a lot of that work. So the CPU doesn't have to do it. So the CPU is basically telling the network card, here's a bunch of data, send it somewhere. And then the card does all the work. But the problem is, Wireshark picks up the packet before it gets processed by the network card. So CPU is sending data to the network card. Wireshark picks it up in the middle, the checksum is not there yet. That's also the reason why you get huge packets or very small packets, because that's everything the network card is doing these days. And so the checksum is broken. You can turn off the acceleration features of your network card if you want to, but why would you do that? You would be making your network card a lot slower. There's a reason why the card does it, because it can do it faster than, I mean, at a 100 megabit network it doesn't matter. With gigabit and more, I wouldn't disable it. Okay? So if you have seen that feature or haven't seen that feature, I can show it to you. It's on the network cards. Everybody knows this kind of dialog, I think, at least if you're using Windows. So let's go maybe to the Wi-Fi, configure, and in the advanced tab, you have things like offloading. Maybe not for a wireless card, that is not a good idea. Where's the other one? Let's take a look. I hope the VMware adapter has it as well. No. But if you have a normal network card, a wired one, which I don't have at this laptop, there will be a feature for offloading, checksum calculation, that kind of thing. It's always turned on. You can turn it off if you want to, but I wouldn't recommend it. It's making things slower, and also it's changing the situation quite by a lot. So if you're doing that, what you're capturing is not what you would be capturing in the correct situation. So better capture with an additional device. That's always what I recommend. Okay, good. So back to the trace file. So bad checksums, get used to them. There are quite a lot. Most of the traces I get, if I don't capture them myself, have bad checksums somewhere, because everybody captures them on systems that are part of the problem, which is not a good idea, but people still do it. Okay, so what happens next? Packet number 5. What's that? Zero window? We had that in the SYN-ACK packet already, didn't we? It means, hey, yes, the handshake is complete, we had a SYN-ACK, everything is cool, but still, don't send me anything. So, what do you think? Is that useful? If I want to talk to a server and the server tells me, yeah, let's have a connection, but let's not talk? That's not useful, right? Okay, why is it doing that? That's the big question here. And to get around that, maybe, is the question of, yes, the server is saying, don't send me anything, but for how long is it keeping that up? Does that change at any point in time? Is there anything in that capture file where the server basically tells us, hey, now we can talk? Oh, who was that? Yeah. The TCP window update in the next packet. So in packet number 6, we have a so-called TCP window update. And that means that now the server says, hey, I can receive, I don't know, 2048 bytes. Is that a lot? 2048 bytes? No, but it's at least 1.5 packets, so to speak. 2048 is a strange number again, because mostly windows are a multiple of the maximum segment size that we have. I hope you ever heard about the maximum segment size. That is the amount of TCP payload that you can send. It's usually 1,460 bytes or less. And the window is very often given as a multiple of that number. So you see like 1,460 bytes or 2,000, I don't know, multiple, 2,800 something, but 2,048 is an odd number. It basically means I can receive one full packet and a little bit more. And that is something that gives away a bit about how old this machine must be. It's something that tells you this is older than normal. Again?
It doesn't use window scaling.
It also doesn't use window scaling, and window scaling is another mechanism to be able to receive more data in one go. The window scaling is only negotiated in the SYN-ACK and SYN packets, and we can see down here that our client has the options of no window scaling, and the server also has no window scaling. So we are limited to a maximum window of 64 kilobytes. We can't do more than that in one transaction. Yeah, but that's not that important. Right now, this is just that, yes, the zero window is raised at some point. It's going up to more than zero, so finally they can talk, but not a lot. Yeah, but then again, servers very often only give you a small window because they don't need to receive that many data. Very often it's only they get a request and then they need to send a lot of data. So the window size is only really relevant for the receiver that is going to get a lot of data. In this case, the server is just saying, hey, I have 2048 bytes, so that's not a lot. And then after the window update, they start sending packets back and forth, not that many things, and then it's over already again. So the big question now is twofold. Is that a good connection? No, because it's taking way too much time to get things done, right? Normally a connection like this should have it's, 20 packets maybe. That should be done in a couple of milliseconds or even microseconds. Here, how long does it take? We have a time column for that, which is off to the left right now. And it's only giving me delta times, so let's change that column preference to something more useful. Seconds since beginning of the capture. So it's taking 4.3 seconds for the whole thing. Like I don't know how many packets there are, but it's not a lot. 15 packets. 4.3 seconds. This is really bad. That's like taking forever. But we lost a lot of that, or most of it, at the SYN being retransmitted. So the server was like deep asleep probably, very surprised that somebody would send a SYN, needing some time and coffee to wake up, and then reacting to the second SYN. This is something you can see by coming from devices that are sort of asleep. So there's devices that go into sleep mode and they get a packet and they're like, oh, wait a minute, I need to... And by the time the client resends its SYN, and then the device is up and ready and had his coffee or Red Bull or whatever, and then it can answer. So the question is, what about the zero window? What is that about? Does that make any kind of sense? Like waking up, saying, hey, here I am, but don't talk to me? Probably still coffee in hand, like I need to drink first? Normally it doesn't. Yeah? So the big question is here, why would a system do that kind of thing? Congestion? Yeah, maybe it's overloaded or something, but no, it isn't. This is the only connection that it had at the time. Any other ideas? It's a little mean, I have to give you that. It's something where I can recommend being the one who did the capture to know what was captured. I think that was one where I was doing the capture myself, so I know what was going to happen or what was happening. I knew the devices. The server here is not a server, it's a printer. And it's a really, really, really old printer. Do you know where you can find the oldest printers everywhere? In a hospital. Because they have these thingies that do the kind of thing. So if they have an Ethernet port, you're lucky. Sometimes they don't even have that. So this is a printer like that, and he's totally surprised that somebody wants to talk to him, and he's like, wait a second, I need to... And then he reacts to the SYN and sets the SYN ACK back, but it says, zero windows, I need to spin up my mechanical things and get everything, because it doesn't have a cache. It's so old, it doesn't have a cache. So it uses the zero window trick to get some time while letting the client know, wait, we're going to do something for you, but please wait, I need to get things going. And at that point where the things are spinning and the printer's ready, then it sends a window update and says, okay, go, let me know what you want from me. And then usually a print job follows with more data. This is a small one I picked because this is basically just checking the printer to see is there whatever problem. I don't know. I don't even know what they're doing in there. I only know the printer was quite surprised by being contacted by anyone. So he was like coming from deep sleep, waking up, saying, hey, stop, I need to prepare myself first. That is why there's the zero window thing. And as soon as it's ready, we can continue. And that's basically what's happening in this trace. Yes?
In this case, why would the server send the zero window when it's already sent in the SYN ACK that it's window zero?
Because there's the ACK coming back, and it reacted to that. Yeah, it could just have stayed quiet, because now, after a three-way handshake, if we are talking to each other, and I say hi, you say hi back, and I say, well, great that we're talking, the next thing you would usually do is wait for me to ask you something, because I was the one trying to talk to you. So that could have happened here. Very often you see that with web servers, that you have a three-way handshake, and then the client is the next one talking. In this case, for some reason, this thing said, well, by the way, I'm still having my coffee, and don't bother me. Yeah. So that is a cool situation, and the solution to this kind of thing is buy a new printer, and then the hospital will say, yeah, but they don't do the thing, so we don't have 5 pages being printed in one go, so we need to keep this. And then I'm like, yeah, what do you do if it breaks? And they're like, we don't know, because we can't get any replacements anymore. Typical situation. If you want to see really bad, is somebody here from a hospital? Okay, no enemies then. If you want to see really bad networks, go to hospitals. If you're going to have surgery, don't go and see what they have for networks, because you won't have surgery there, at least in Germany. All right, so any kind of questions still open about this one? You don't need to ask right now. You can also talk to me later. You can ask by email. You can ask on ask.wireshark.org later. So if anything comes up at a later time, just ask. It's no problem.
I do have one question.
Yes?
The checksum?
Yeah, the checksum.
If when I capture, I log to disk,
Mm-hmm.
I don't want to log the payload of a packet.
Okay.
But I want to know at least the check. Is there a way to maintain the checksum value as it would have been?
So the question is, if I capture to disk and I don't want to keep the payload, which is a reasonable request because for privacy reasons or for disk space reasons, performance reasons, whatever, usually I would recommend keep all the headers intact, which means you should keep Ethernet, IP, TCP, which means you still have the checksums. The checksums are in the headers, so if you're cutting off the payload, you will still have them. So that should not be a problem. Yeah. Or no, correct. If you don't have the payload, you cannot calculate the checksums. Yeah, so that is a problem. Good question. So if you capture something and you cut away some payload bytes, no more checksums for you. Because for checksum calculation, Wireshark, of course, needs everything. Because otherwise, how to calculate it? But the IP checksum for the IP header is just calculated for the IP header, and that is still correct or not correct. But if it wouldn't not be correct, and I wrote a blog post about this, if you have broken checksums on your network, what will happen is that the network card receiving the broken packet will already discard the packet. You will not see it in your capture anyway. Unless you have a very expensive capture card like Napatech, Endace, whatever, they will still be able to give you even the broken frames. But they will tell you, hey, this one was broken. So once again, you have the information. Okay, so I have no idea how much time I have left, but Angelo will stop me at some point, I think. I hope. We don't know. I think I've been talking for almost 50 minutes now, so. Yeah, so I have 50 minutes wasted already. And I have 4 more trace files. I don't think we're going to go through all of them. But not a problem. We'll check out the next one. The next one is, I think, even shorter. We can try to look at it this way. Okay, what do we have? Yeah, there's ARP, basically telling you this IP is for that MAC address, stuff like that. Any problem up there in the ARP protocol? There's a retransmission for some reason, yes. So let's say we start at the ARP things. Anything that looks strange to you? Such a fun trace because everybody's sitting there like, there must be something wrong because he has it in there. No, there's nothing wrong with it. It's just in there to have me make this joke. The ARP is fine. Don't care about the ARP. Yeah. So what you're going to learn when you're doing network analysis is skipping over things that are not relevant. Okay, if you're starting network analysis, you'll be skipping over things really slow, like, is this normal, is this not normal, I don't know, it's wasting time. If you see me or Christian going over network traces, we're scrolling like crazy, like, I don't care, I don't care, I don't care. Thousands of packets passing by because we can spot almost immediately, also by colorizing them, that doesn't matter, it doesn't matter, it doesn't matter, it doesn't matter. Stop, there it is. And everybody around us is like, how did you? Well, yeah, I've seen it enough times. It's just experience. So in the beginning, you're slow. You're thinking, hey, there must be something because it's in there. Not always is there a problem. So in this case, the ARPs are fine. The problem is in the TCP stuff. So we have 4 packets to look at. The first packet, let's do it one by one. The SYN packet, anything strange? Well, it's green, isn't it? Cool, it's good. The second one. What's happening with the second one? I think it's red again, isn't it? Sort of. Let's check out what my rule is. For this one. Oh, it's kind of dark orange because of the rule name TCP without don't fragment flag. What does that mean? Hmm?
It's not bad, but it's no longer really used. Now we don't want packets to be fragmented, so in modern systems, you always have don't fragment set.
Yeah. So what usually should happen is that if you look at the IP header, there should be a flag telling me here, don't fragment. That should be set for each and every TCP packet. TCP is never fragmented. Okay, fragmentation, you guys know what fragmentation means? It means sending a very big packet, or not really very big, but too big for the next hop, so the router, however you want to pronounce it, is allowed to cut it in smaller pieces so that they fit through. That is only possible if the don't fragment bit is not set, like in this case. Here it's not set, so if I send a packet that is too big, like this, a router can fragment it. TCP should have this flag set. TCP packets should not be fragmented. So this is something where somebody messed around with the TCP settings or something else and cleared the flag. And this happens a lot with firewall administrators who are not that really great at their job because they don't know what MTU really means. So they're clearing the flag to get rid of a MTU problem that they don't know how to solve otherwise. And that is the most common thing. So if you see something like this, somebody messed around with a workaround that he shouldn't have or she shouldn't have. So the coloring rule basically tells me somebody messed with the flags. There should be a don't fragment flag here. We can see how it's supposed to look like in the SYN packet because there it is. It's not set. It's set, so it's not allowed to fragment this one. This is the correct flag setting for a TCP packet. And the next one is not correct. It's basically allowing fragmentation, which it shouldn't. This is why this is orange. Okay, so what else? We see in the packet number 5 another SYN. Why would we see another SYN packet? Because we see that there's a SYN, there's a SYN ACK. What kind of packet do we expect now? Should be an ACK, right? But there's no ACK, there's another SYN. Why? That's the source, never got the SYN ACK. Yeah, that means we need to keep in mind that we have two stations talking to each other. One is sending the SYN, the other one is sending the SYN ACK, but we don't know where this one was captured. It was maybe captured in the middle, and the SYN ACK was still alive at that point, but it never got to the final destination, so the final destination said, well, I need to resend the SYN, and there's another good indicator for that kind of thing, why it resent the SYN. It didn't receive or like the SYN ACK. That's another possibility. It can also not like the SYN ACK. And there's a 3-second timeout again, resending the SYN. So resending the SYN is basically this 3-second stuff again. So I can tell you this one was captured on the system that sent the SYN. So sender of the SYN, the other guy, SYN was sent, SYN ACK came back and was received on the sending side. So we know it was there. Why does it still send another SYN? okay, we know that the SYN shouldn't have been sent, but it was sent, so the reason for that can only be that the SYN egg somehow didn't do what it should have done or wasn't okay. It arrived, so the first idea of why it would resend the SYN is not right. So what else could be the reason for another SYN to be sent out? Who? Corrupt packet? Okay. Why do you think it would be corrupt?
Many reasons, few bytes clipped or something.
Yeah, the most obvious one is what Flood just said. The checksum is broken. So this is me being really mean because I just walked you through an example where the checksums are broken, but it's not a problem because they were broken on capture. This one is an example for a checksum really being broken. Okay? So here the checksum is broken, which is why the SYN egg is incorrect. The sender of the SYN says, great, I got a SYN egg, but this is not correct. It's damaged somehow. Drops it. Nothing else happens. There's no new SYN egg coming, of course, because the sender sent the SYN egg and it arrived broken. So another SYN is sent. In this case, it's of course, or not of course, but in this case, it's the broken checksum that causes the SYN to be resent. Okay, so then at some point we have a reset here. And that is interesting again because this reset packet has a sequence of 0. And I think it's, I don't know if I'm toggled relative sequence numbers. No, it's an absolute sequence number. As you can see, relative sequence numbers here is not checked. So this sequence number here, and for this we can also go into the packet bytes. Where are they? They're somewhere to the left, I think, or down there. Clicking on the sequence number, you can see the sequence number in the packet is 0. So this guy is sending us a SYN egg where the checksum is broken. This guy is also sending us a reset with a sequence number of 0. And now the question, who's the bad guy in this situation? Is it the one sending the SYN? Who thinks it's the one sending the SYN? Who thinks it's the other one? And the rest is like, we don't know. Yeah, well, in this situation, it's the guy sending the SYN egg and the reset. I don't know what this thing is doing, but it's doing broken stuff. And this is something that showed up a lot more in the recent couple of months and years even, because we have this wonderful thing called IoT now, Internet of Thingies. And with Internet of Thingies, there are really small devices, and everybody thinks you can program a TCP stack, which they can't. They don't know how to do that, or they try, but it doesn't really work. So we see a lot of those things that we thought would be a thing of the past because all the network cards are now mature. Windows, Mac OS, Linux, they all know how to do it, yes. But then the Internet of Thingies came up, and they're like, okay, let's try it again. And they built broken stacks. So we have a lot of questions on askwireshark.org where people send us things like, why isn't it doing the handshake correctly? Why is it doing that? And very often the reason is because you programmed it wrong. Yeah, the guy asking programming something and didn't get it quite right. So writing a TCP stack is not an easy task. That is really complex. So if you want to spend a lot of time on something very interesting, go write a TCP stack. Because there's so many things that you need to keep track of. And a lot of people even get the basic thing wrongs, like correct checksums, sending correct sequence numbers, stuff like that. Very often because they don't know how it's supposed to work. And then we get traces like this. So this is broken and another example of a bad server. Okay, any questions to this one? Once again, if questions come up later or you're revisiting the traces at home and have something, just let me know. So let's go to sample number 3. I have no idea what that one was. Okay, another syn egg in red color. Why? What's wrong with this one? I'm not going to show you the color rule because that would be giving it away. What's wrong with the syn egg? It's red. Why? Again? Window size, it's 0. Yeah. Again, one of the things. Hey, let's talk. Yeah, let's talk, but don't talk. Okay, so that stuff happens a lot. How did I find all these traces? I mean, how many times have you found a trace like this? Not that many times, right? Well, twice? Wow, great. Me, yeah, I find them all the time. But the reason is I'm looking at traces every day and I see things like this, and I have a color rule telling me things like this. So if I don't have my color rules, I would not see it probably. But with colorization rules, this is easy to spot. I just see the red color and then it's just like, what is broken with this one? And then I see it usually really quick. So having good color rules is very nice, helping you in ignoring the typical stuff and just looking at the bad stuff. But it's also something that you need to be careful of. If you download my color profile and use it, which you can do, don't think that everything that is colored is bad and that the things that are not colors are not bad. It could still be bad in the one end or not bad in the other end. It's up to the analyst to decide that kind of thing. But it's like a helper. It's like an arrow pointing there. Look here, look there. You probably don't need to look here. That's what the color rules are for. Okay? So, 0 window, yeah. But then in the 4th packet, we get a window of 496. And now something that is a little more advanced would be, how bad is the 0 window in the syn egg? How much does it hurt us? How do we measure hurt or pain in a trace file? What's the one measurement that you have to measure pain giving you or displayed in a trace file? There's one thing, and that is time. It's the only rule. Yeah. If you have a trace file with 5 retransmissions and they cost you a total 3 seconds maybe, which would be like forever, those 5 retransmissions are really bad. If I have a trace file with 5,000 retransmissions, they cost you half a second, it's like, yeah, whatever. Okay, so timing is the one thing that you need to look at, and the question here is, does the 0 window hurt us that much? How much does it cost us? Yeah, it's like, I mean, in the 3rd packet we have a 0.39 for the milliseconds, so yeah, users won't even notice probably. It's like the thingy turning around in Firefox is turning around half a circle more than usual, but it doesn't matter. So, handshake, is it a good one or a bad one? It's not the perfect one, but it's okay-ish. I wouldn't look at it that much. Yeah, so it's all right. So there must be a problem here because otherwise I wouldn't have brought the trace. Let's find the problem, right? And let's do a fun thing again to show you how useful color rules are. I'm going to go to the default profile again. Any problems? Looks like there are problems, right? What is the problem here? It says frame check sequence incorrect, should be something. It's 0. If you see checksums that are 0, what does that mean? It's probably not a broken checksum, it's something else. In this case, for whatever reason, there are zeros at the end of the frame, and Wireshark thinks it could be a checksum. But it's not really a checksum, it's just some bytes there. We can find the bytes that are responsible for this quite easily, because if you click on the transmission control protocol, which is the last protocol in this thing, you will see that it highlights the bytes making up the TCP protocol, and there's zeros following it. I have no idea why. This sometimes happens. But if the checksum for the Ethernet frame would have been really bad, what would happen? The network card would not have accepted the frame, it would have dropped it. So you don't see broken checksums for Ethernet frames in a capture, unless you have a professional capture device that captures the frame check sequences, and then they're not zero. Yeah, being zero and in a normal capture done on a non-professional capture card, ignore it. Yeah, you didn't see it in my color profile because I didn't care. Yeah, frame check sequence errors are, I don't care, because they are not going to happen in most situations anyway. All right, so we ignore the frame check sequences. I think we can also tell Wireshark to do not validate the Ethernet checksum if possible, and now it looks much better. Okay, see anything that is strange? Stop me when I'm coming to a location where something is strange. Everything's good, 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 good. Oh, what was that? Interesting. So I don't know about you, but I really hate these colors. I don't like colored backgrounds. It's just me. I don't know about you. So what I'm going to do now is go back to my profile, because it's much easier to read, I think. No, not this one, the other one. Oh, it jumped up. Okay. Whoa. There we go. Okay, what is happening here? And I think I can remove that one again and make some room. So what do we see here? We see something working great, apparently no colors, no nothing, and then suddenly red stuff. What happens just before the red stuff? What? Finac, session finished, thank you, goodbye, we're friends, let's go. Okay, next thing happens is what? What's the packet number 1044 doing? This one. Window size, looking good? Yeah, okay. Sequence number, yes, they're there. TCP length, 0. Maximum segment size, 14 something. What is that thing in the front? TCP port numbers reused. What does that mean? I have to come over and repeat it because nobody else will hear it.
Means that the ports the sender is trying to communicate to is, the receiver is trying to use a port that's either in use or recently used.
Okay, so the answer he gave was that the port is being reused or is still active somewhere else. So Wireshark basically tells us there's a communication using the same IP address port combination that we've seen before. Where did we see it before? It's really easy. In the last connection. So the connection before this new connection, and that is something that is sometimes annoying because you can see there's a SYN in the packet 1044, but the TCP port numbers we used moved it slightly to the right, so sometimes it escapes the focus. You don't see the SYN because it's a little more to the right than you are used to. This is a new connection starting, and it's using the exact same IP address port than the previous connection. How do we prove that? Real easy. There's a real easy way to prove that this is the case. and that is what I'm doing now, is filtering for it. So I'm doing a conversation filter for the TCP connection, like this. Who's ever used that kind of filter? Conversation filter TCP? That is the most important filter you should be using at all times because it's isolating one single TCP connection. There are people who are using follow TCP stream. Who's using follow TCP stream? Stop using follow TCP stream, because what you're doing is you're doing the same thing but clicking away this annoying window that pops up and then start working here. Please start using conversation filter TCP. Much better. Because if you do this, you will see that now I have a filter for IP address 192.68.0.1 and 10.10.10.1 and port this and port that. And how many connections do we see? Well, I'm zoomed in so you can't see. But you'll see that this filter is giving you the old connection and the new connection. So this is proof that we have two connections at least using the same IP addresses and ports. Is that allowed? The correct answer to this one is the typical one that is, which one is it? It depends. That is the standard answer you can always use in a question like this. It depends, because mostly, or almost always, it depends. The problem is, I will ask you, on what? So you can only use it depends if you know what it depends on. Otherwise, it's not a valid answer. Vlad knows what it depends on, so he can use it. I don't know if everybody else knows what it depends on, so maybe be more careful with it. Okay, so it depends. On what does it depend? On the timing. Because think about this. Two stations talking to each other for weeks, months, years, whatever. Are they allowed to reuse the exact same IP addresses and ports? Yes, because how many are there? There are 64,000 ports on the client side and a fixed one on the server side. So at some point you will wrap around and start using the old ones again. And if we prevented that or forbid it, at some point you will be like, I ran out of ports, I need to reboot or whatever. But so it depends on the time distance from when the old port was used last. And that is something where we go into TCP states and in what state is the TCP connection. Is it still open? Is it not open? Was it closed? Whatever is it? So is it open at this point in time when the SYN comes? Who thinks it's still open? Who thinks it's closed? Okay, the rest is like, I don't know. I love binary questions because very often it's like, and the rest is, half of them is missing. Yes, it's closed, kind of, because we've seen the fin, ACK. So this is perfectly shut down, like fin, ACK. That's textbook shutdown. Why are we having a problem here? And for the fun of it, take a look at the packet in number 2047. What do you see there? Port numbers reused again, right? Does this one work? Who thinks it's working? Good. It's obviously working because then there are SYN, SYN-ACK, whatever, it's working. Why isn't the one between the two working? Yes, short time is one of the things. Let's check what the time difference is between the fin and the next SYN. How much time is gone past? 17 seconds. Well, 17 seconds is like an eternity, but not in TCP stack timing things, because they're like, hey, when you tear down a connection with a fin-ACK, let's wait for 2 more minutes if something is still being sent around the globe and comes in later. That's like an eternity. 2 minutes, that is the so-called time wait state that TCP stacks sometimes have. It basically means like the port is almost closed, but not really. And so you can't use it again. So we have to wait 2 minutes before we can use it. Okay? If we do fin-ACK on a standard stack, 2 minutes before we can reuse the port. So when is the port being reused when it works? How much time has passed? 2 minutes? Yeah, let's do a little trick. We just put a time reference on the last ACK here. Yeah, with set unset time reference, you can put a 0 indicator on the time. So it starts from 0 here. And we can see the working SYN is at 42.4 seconds. The non-working SYN is at 16 seconds. So why is the second SYN working when it's not the full 2 minutes that we needed? Why did the second one work?
Someone has changed some configuration.
It could be a configuration thing, that somebody reduced the time wait state to the minimum, which would be 30 seconds. That's the smallest, at least on Windows, that you can set. On Linux, of course, because the Linux guys are much more configurable in anything, you can probably set it to a second or something, which is not that great of an idea. But with Windows, at least, it needs to be more than 29 seconds. Let's say it needs to be 30 seconds or more. So the first one, yeah, it's still too fast, but the second one could work, but it's not the case in this one. The question is it the reset? And you were? There's no firewall that is responsible. This is just the end station not accepting this. Yeah, but a firewall would be another idea. Always check for devices in the middle. That is very often the thing, that we get traces and we say, there must be something in there because this behavior is very strange. But this here is just the end station doing this, and your idea was the reset. What happens if you get a reset? Compared to a fin-ACK, what is the difference? Again? Immediately. A reset means shut up, session is gone. No time wait, no nothing. So if you ever wondered why Microsoft started using reset instead of fin-ACK, it's because the session is dead instantaneously. No more time wait, no more open whatever, no more socket reuse problems, resources being kept in memory. A reset means this session is finished now. And what happens here in this trace is that the guy is trying to reuse the socket, and the other one is like, no. And then the reset comes in, which clears everything away, and then the SYN works. Yeah, so if he would have ended the previous connection, not with a fin-ACK, but with a reset right away, the first SYN retry or the port reuse would have worked right away. But because of fin-ACK, it didn't. Okay? So the problem here is port reuse is something that you see sometimes when there's a lot of connections, and they can be a problem, but not always. It depends on if the old connection was torn down correctly, fast enough, and the time between those. I have traces where there's port reused dozens and thousands of them sometimes, but there's a half an hour between them. So it's like, we don't care, we don't care, we don't care. It always depends on the relationship to the previous connection. So port reuse is something you should look at. Just check out, well, when was the old one ended? Was it ended with a reset or with a fin? If it was a fin and it's too close to each other, it may fail. If it's with a reset, doesn't matter.
What was the default standard?
Default standard is 2 minutes. There's a registry setting in Windows that you can use to change it down to 30 seconds, but that's the minimum for Windows at least. Yeah?
Even after your both sides close the connection for a handshake, still the client was listening to that port.
Yeah, the client or the server, I don't know who tore it down, but the server one still had the connection in its table.
Still it's thinking.
Yeah. So if you do a netstat on the command line, you will see that this port and IP combination is still in time wait state. Now, if you see net state time wait, this thing is still not being able to be reused. Okay, so many people are coming into the room. It must be because I have to be done, I think. Yep, okay, so I think we got through 3 of them, but you can work to the others if you want. Ask me questions during the conference or later. I didn't try to get through all of them. I just wanted to make sure I have enough of them and spend enough time on all of them so that you're kind of happy with what you learned and not being rushed through everything. So I had more than I wanted to show. So don't feel bad that we didn't get there. I got through all of them in the US and people were like, oh my God. So I took it a lot slower now, trying to basically get the things across. I hope you learned something. You had some fun. Use traces. Read my blog if you want to. There's a lot of these things that I have here are explained in greater detail. I write my blog as kind of a reference thing. So if you want to look up checksums and why you can capture them and what the problems are with port we used, I have a blog post for almost everything now. Just find it, and if there's still questions, send me an email, send me a Twitter thingy, talk to me on SharkFest. I'm here for the rest of the week, and thank you.